Now, hello everyone. Welcome to our presentation. We are from Department of Computer Science at University at Buffalo, and we're going to present on secure vascular biometric recognition. So let's look into it. To talk about the abstract, the vascular features differ from the traditional biometrics like fingerprint, as they are much more difficult to be tampered with. In this paper, we propose an end-to-end vascular feature recognition system, combining with traditional pre-processing techniques to enhance the features and a deep learning model to extract the features and finally biohashing the template to provide added security. To summarize, our core model achieved an accuracy of 95.58% and an EER of 0. We would be looking at a detailed implementation in the upcoming slides. Like I mentioned, we combine the traditional pre-processing methods CLAHE and PCA to enhance the image quality, followed by utilizing a ResNet50 model to extract the finger vein template, and we would be going through a biohashing algorithm in detail. To talk about the data set, so we made use of the finger vein USM, FAUSM database, which consisted a total of 5,904 images for 492 finger classes. So this comprised of 123 individuals with 83 males and 14 females, and 4 images for each individual: left index, left middle, right index, and right middle. So all these images, each image was captured in 6 times in a session, with 2 sessions with 2 weeks gap between them. So in our approach, the first session of images that were captured were used for training, and the second session of images were used for testing. So this is an example of the sample images from the data set, as you can see. So now let's look at the algorithm that we propose. First, the input image is pre-processed with CLAHE and then CLAHE and PCA and fed into the ResNet50 model, which is a feature extractor. Here, the triplet loss encourages the model to learn discriminative feature embeddings by minimizing the distance between matching finger vein samples and maximizing the distance between the samples that do not match with each other. The experimentation was tested on embedding sizes of the template with sizes 512 and 256, and we have provided a finding as an abletion study in the upcoming slides. Once the template has been extracted, the extracted template is biohashed to protect it against the imposters. We will be looking at the details of the biohashing algorithm that we had implemented in the upcoming slides too. So let's talk about the pre-processing methods that we have followed. The first thing is the images are pre-processed with CLAHE with a block size of 8 and a segment limit of 40. So this is used to improve the visibility of details in the image by enhancing the contrast, bringing out relevant features, helping the model to better discriminate the finger veins. The median filter was used. It was a 3x3 nonlinear filter to reduce the noise dimension present in the image, followed by the principal component analysis, which reduces the dimensions of data while still preserving the important information, allowing the model to train at a faster rate and also better extract the relevant features in the image. So these are some examples of the pre-processing results that we obtained. As you can see, this is the original image from the data set, an histogram of the image, and the CLAHE output, as it's clearly visible that the veins are much more clearly visible when the image has been pre-processed with CLAHE. And the median filter is added to denoise the image, followed by the principal component analysis on top of the CLAHE pre-processed image. So in terms of training, like I already mentioned, ResNet50 was a feature extracted in this. So all the trainings that we performed were on the ResNet50 model, and we performed training with 4 different stages. The first and second one were with the images pre-processed with CLAHE alone, with an embedding sizes of both 256 and 512. And also the images pre-processed with CLAHE and on top of it PCA, with both embedding sizes of 256 and 512. Although we haven't specified explicitly, all the above pre-processing also involves median filtering in them. So this depicts the training results that we observed at the end of each training method. So as you can see, the model pre-processed with CLAHE and PCA with an embedding size of 512 had the least loss among all the 4. So now let's look at the biohashing algorithm that we followed to biohash the template. So in this case, the input would be an unprotected template, which is technically the template extracted from the model, a user's template. and a random seed value. So this random seed value is generated based on the user's label, using which a pseudo-random vector is generated with the template's shape and the length of biohash as an input. In this case, we set the length of biohash as 100. The vector further undergoes QR decomposition, resulting in an orthonormal vector Q, which allows better feature extraction by identifying the relevant features and representing the most distinctive characteristics of the biometric data. Further, the dot product between the orthonormal vector obtained and the template is computed. To find the threshold of this, to find the threshold of a biometric template, we calculated the mean of the dot product, and this mean was used as a threshold for the biohash templates. So the reason for using this mean as a threshold or not just some static value by trial and error process is that this algorithm can be applied to biohash any kind of vascular images, for example, palm or dorsal images. Finally, the new biohash template bit is set to 1 if the DI value is greater than the threshold. DI here represents the dot product values that are obtained. So if it is greater than the threshold, the biohash template bit is set to 1 or else it's set to 0. So in case of matching algorithm, the user's extracted template and the template stored in the database is compared using Hamming distance. So if the extracted user's mean template at least matches for 90 bits out of the 100 bits, then the user has been cleared for access or else he would be flagged as an imposter. Again, this threshold for the matching algorithm can be adjusted based on your needs. Now let's look at the results that we observed after training and evaluating our model. So as you could clearly see that our proposed model has a slight reduction in accuracy compared to the state-of-the-art models observed. But you should also note that the EER of the first two state-of-the-art models is pretty high compared to the proposed model, which has an EER of 0. And there has been no documentation of the EER of the third model. So this clearly shows, although there's a slight trade-off in accuracy, but the protection from the biohashing is pretty good as the EER depicts a value of 0. Now, looking at the ablation study, as I mentioned, we conducted experiments on 4 different types, including the different pre-processing and embedding sizes. The images pre-processed with both CLAHI and PCA with an embedding size of 512 achieved the best accuracy of 95.57% across all the other methods that we followed. Now, to highlight the importance of biohashing the templates, we performed analysis before and after biohashing. From the first chart, we could infer that the number of there are 139 imposters who have been actually predicted as legit users and having gained access. So after biohashing, the number of imposters who have been predicted users are literally 0, which indicates how efficient the biohashing is. Although there is a very slight trade-off to this, is genuine users getting predicted as imposters is 862 after biohashing, whereas genuine users getting predicted as imposters 163 before it. So this can be attributed to the high threshold value we set during the matching algorithm using Hamming distance. So based on your use case, you can actually change the threshold value to tackle this trade-off. This depicts the ROC curve indicating the performance of a core model, which is basically the images pre-processed CLAHI and PCA with an embedding size of 512. To conclude, the method that we propose incorporates the traditional pre-processing methods to improve image quality and a ResNet50 model to extract the vein patterns and further biohashing the template to provide added security. Some future areas of improvement would be to experiment with different or better models and also to test this method on different vascular images dataset and see how well they perform. Yeah, so this is our presentation. Thank you for watching.